Welcome back to 8.3 Geometric Sequences series. This is part 2. Just a quick review here. For geometric sequences, we have a common ratio between terms, such as multiply by 4, multiply by 4, multiply by 4. Down here, we have to figure out our ratio, we have to check if it's geometric. -6 divided by 9, 4 divided by -6, -8/3 divided by 4, which we discovered all of those became common ratio. It's actually negative here. All of those became negative, so the common ratio is -2/3 here. And here apparently 2/7 divided by 1/5 was not equal to 3/9 divided by 2/7 or to 4/11 divided by 3/9. So it was not geometric, but that's what a geometric sequence is. And we went through on video 1, part 1 of this, how to find an nth term. What we did not cover yet were these formulas for finding sums of the first n terms. Or in this case, believe it or not, infinity terms, we're going to find that sum. It doesn't necessarily have to be infinity or negative infinity. We'll talk about that. So first off, up until this point, you've had 3 formulas that we talked about that you need to know why the formula is what it is. Finding the nth term of an arithmetic. If we had an arithmetic, the nth term is equal to the first term. What do? We just start adding on to it. We add on the same amount. That's called the difference. And how many times do we add it on? Well, it depends on how many steps we take. And the number of steps from the first term to the nth term is n minus 1. And then the sum of the first n terms of an arithmetic is equal to the first term of the arithmetic plus the last term of that arithmetic sequence divided by 2. That gives us the average term. And if we take the average term by the number of terms, we've got the sum. And then in this section, the geometric, so we should understand these formulas. The nth term is we start with the first term, and now we start multiplying by that common ratio. How many times do we multiply by the common ratio? How many steps is it from the first term to the nth term? For instance, down here, term 1, term 2, term 3, term 4. To get to the fourth term, I multiplied by 4, but only 3 times. 4 minus 1, that's how many steps there are. That's a biggie for us. But these formulas are not ones that we're going to try to make sense out of. These are going to be, we're just going to commit to know the formula. One thing nice about these 2 formulas, they both have A1 as a factor, which could be in the numerator in both cases, and they both are on 1 minus r. The only difference is this has a numerator of 1 minus r to the n. Now if we take a look at this, for the sum of the infinite sequence, another way of saying this is to say -1 is less than r is less than 1. So r is a fraction between -1 to 1, or a decimal between -1 to 1, which could be a fraction. But it's a smaller value, which means each step the value is going to get closer and closer and closer to 0. Now imagine as r gets close to 0, let's say r is just a half. If I take 1/2 just to the third, it becomes 1/8. To the 10th becomes 1 on 1024. This is becoming virtually 0. As n would go to infinity, this little guy right here would approach 0. And that would make this become a1 times 1, a1. If this approaches 0, never really gets there, but as this approaches 0, it would just be a1 times 1 on 1 minus r. So to be honest, they're the same formula, but I think we just want to memorize these separately from one another. So with that, let's take a look at some problems here. We're going to jump to number 58, where we had left off on the previous video. And here we're to find the sum, use a graphing calculator to verify your results. So I'm going to just start thinking about my terms. When I is 1, the first term is 32 times 1/4 to the 0th. 32 times 1/4 to the 0th. 1/4 to the 0th is 1 times 32. It's just 32. When I is 2, I get 32 times 1/4 to the 2 minus 1 first, and I get 8. And each term after that I'm just going to multiply by, I'm going to increase this exponent, I'm just going to multiply by another 1/4. So this would be plus 2 plus 1/2 times a fourth plus 1/8 plus 1 on 32. And I've got my 6 terms and I could add those together. But if I gave this problem to you on a test, this would be more like to the 60th. I would have a big number in there to make this inconvenient for you to do without knowing the formula. Very inconvenient. It might be the 600th. Okay, so our formula was sum of the first, how many terms do we have? 5 steps from 1 to 6. So 6 terms. We've talked about that a lot. Sum of the 6 terms equals, remember, it was the first term times 1 minus our ratio. Our ratio is 1/4 to the n, our number of terms, 6, all on plain old 1 minus 1/4. And if you've got a TI-84, there's a good chance you have the capability to enter this as fractions. Otherwise, you have to use some extra parentheses. So I'm going to go 32 times second or alpha y n on d. I get 1 minus, I could enter this as 0.25, but I'm just going to enter as 1 divided by 4 raised to the 6th on all of 1 minus 1 divided by 4, kind of as it appears. And we enter, and it gave it to me as a fraction, and that's great, and maybe we're fine with that at times, so I'm going to jot that one down, equals 1365 on 32. If I just went 1365 divided by 32 here, I would know that I could write this as 42, and I'm going to subtract away the 42, and I'm going to math fraction again. 42 and 21/32. We haven't talked much about that, but I think hopefully that makes sense to you. Okay, careful here. What do we need to know then? Here's our formula. The sum of the first n terms equals the first term times 1 minus r to the n, all on 1 minus r. That's our formula. So I need to know the first term, I need to know the ratio, I need to know the number of terms. So A1 is what happens when I put 0 in for n. I get 500 times 1. 500 is the first term. What is our common ratio? I think that's really, really clear. Each time we're going to multiply by an additional 1.04. What's the number of terms dangerous here? I called out in class for this, and about half people missed this. How many terms are there? You don't want to think in terms of terms. You want to think in terms of steps. How many steps from 0 to 6? Steps is subtraction. 6 minus 0 is the number of steps. If there's 6 steps from the first term to the last term, there's 7 terms, so n is 7. So the sum of the 7 terms equals the first term, 500, times 1 minus 1.04 to the 7th, all on 1 minus 1.04. 500 times alpha y equals on 1, I mean I could put negative 0.04, but I'll just go ahead and enter it just as it appears. And we get just about equal to, and you could go with the exact answer here, but I'm going to use our general rule. If it doesn't specify, we're going to round to 3 decimal places, just like AP tests do. Okay, use summation notation to write the sum. This can be a little bit tricky here, but I can tell that we multiply by 2, on and on. And it really, truthfully, wouldn't take too long to just keep multiplying by 2 and list all these out. But again, if this was a test, I might make this a much, much, much bigger number. So instead of working with, 10 terms or 7 terms or something like that, we might be working with hundreds of terms. So I want you to be able to work with the formulas. So this is the sum as x goes from something to something. Well, we start with 7, and we start multiplying by 2, but we multiply by 2 a number of times. And if I said, let's set x equal, start with 1, I wouldn't want to just put x here because then my first term would be 7 times 2 to the first. But 7 times 2 to the 0th would work for us. And now I have to figure out when I get to this term. And like I said, I could just do this. I could go 56, 112, 200 something, 400 something, 896. We could count our number of terms doing that, but I want to make it not convenient to you. So what we'd have to do is say, okay, we got to 896. We started with 7. We started multiplying by 2. How many steps did it take? Excuse me, how many steps did it take to get from here to here? That would be n minus 1 steps. So let's see, we're going to go 896 divided by 7 is 128. 2 to the n minus 1 equals 128. Well, let's take... right here, we can go ahead and probably just put values in here for 2. How would we solve for n if this wasn't such a finite number here? I mean, if this was billions, we'd have to actually use logarithms here. I'd have to actually do something like, I'm just going to ln it. ln this equals ln that. So we would get n minus 1 times ln 2 equals ln 128, or n equals ln 128. I have to divide away ln 2, and I have to add 1 back onto that. Again, I understand we don't have to do that for this, but there might come a time. So ln 128 divided by ln 2 plus 1. I'm really hoping that becomes an integer. And we have 8 terms here. If I have 8 terms here, I want to run from 1 to 8. And it's worth putting in that last term just to see what happens here. When I put in the 8, I get 7 times 2 raised to the, when 8 goes in here, 7th, and there we go. We've got our 896. Worth checking that. It's really easy to be off by a term. Another way of writing this same thing would be to say x equals 0 to 7 instead of 1 to 8. We still have 8 terms, 7 steps, and this would just be 7 times 2 to the x. Okay, so our common, let's take a look. Is this thing geometric? Negative 3 divided by 15. 3 on 5 divided by negative 3. And yep, our common ratio is negative 0.2 or negative 1/5, negative 2/10, negative 1/5. So we could say x equals 1 to, we need to know what our last term is. And then we're going to have, we start with 15, we start multiplying by negative 1/5. But our first term is plain old 15. I need to negate this, so to the 0th. What's our last term? Now, I'm just going to write these out and show you what you can often do. We've got 15, negative 3. We've got 3/5. I'm multiplying by negative 1/5, so that's negative 3 on 25. Multiply by negative 1/5. Positive 3 on 125. Multiply by negative 1/5. Negative 3 on 625. So we have 1, 2, 3, 4, 5, 6 terms. Put in 6, and we have, oh, and this shouldn't be 0. I'm sorry, this should be x minus 1. So when I put in 1, I get negative 1/5 to the 0th. And worth checking that last term. Let's see if that last term gives us what we're supposed to get up here, negative 3 on 625. So let's go 15 times negative 1 on 5, all of it. 2, though, when I put in 6 here, I get 5, and I didn't want that. Second enter. I wanted this to be raised to the 5, and if I math fraction this guy, I get negative 3 on 625. Definitely worth checking that last term. So that's how we would do this. Back of the book, I didn't check the back of the book. This says use summation notation to write the sum. We've written the sum. I don't believe they're even asking us to actually go through the process of finding the sum. They just want us to be able to do that. Again, this one could have been x equals 0 to just 5 instead of 1 to 6 if we went 15 negative 1/5 to that plain old x. Back of the book might have it written that way rather than this way. Okay, find the sum of the infinite geometric series if possible. I talk about this with, I should have gotten a nice diagram drawn for this. I talk about this as like a frog on a log problem. So we got this frog sitting here. Here's my frog, beautiful frog. And I've this 8-foot log here. I've trained my frog to start at the end of here and jump halfway to the end of the log. And every 5 seconds jump again. So the first jump goes 4 feet. The second jump goes just 2 feet. Third jump goes a foot. And then we go a half a foot. And then we go a quarter of a foot, and an eighth of a foot, and a 16th of a foot, and a 64th of a foot, and a 128th of a foot. When does the frog fall off the log? Should be never. But after just a very few numbers of jumps, we're already almost to 8. Imagine 1,000 jumps, we're basically at 8. Imagine 1,000,000 jumps, we're basically at 8. Infinity jumps, and theoretically, we are now at 8. And that's why, that's what this formula does. This formula right back here, here it is. The formula we're using says A1, the first jump the frog makes, on 1 minus the ratio, that's the sum of all infinity jumps. So that would be first jump 4 on 1 minus 1/2 is 4 divided by 1/2, or 4 times 2, 8. Okay, that's that formula for us. The condition is, though, the frog's jumps have to get closer to 0. It can go back and forth. I can have my frog go 4 this way, and then back a half this way, then forward 2, and back 1, and forward a half, and pretty soon our total distance is going to be somewhere back in here. And that would be where our ratio is negative 1/2. So the key is we have to make sure, they say, if possible, find the sum. Well, is it possible? Yes, because each jump, my ratio is between negative 1. Since negative 1 is less than 2/3 is less than 1, then it is possible. So if it's possible and you've got an 84 plus, there's a good chance you have this feature, alpha window. In fact, I'm going to clear out of here first. Alpha window, I want summation. Oh, but can I put infinity in there? Oh, show you what we could do. We could go x equals 0 to, let's go just to 1,000. Nowhere near infinity, which doesn't even make any sense if you think about it, because it's just as close to, 1,000 is just as close to infinity as 1 is. But now I'm going to put in that formula. Let's go 6 times 2 divided by 3 raised to the x, and we get, it takes our calculator a while to do this too, but imagine doing that one by hand when you have to have 1,001 terms of this. Still thinking I might have overshot this a little bit. I'm not thinking because it's getting real big, thinking because it's just got a whole lot of things to do. I didn't test this before, so I'm just kind of tap dancing right now. And it says it's 18, and I'm going to tell you it is not 18, but it's really, 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 really close to 18. So that probably is our solution. So let's go through the process here. The sum of the first infinity equals the first jump. How long is the first jump? Put 0 in, and we get 6 times 2/3 to the 0th, 6 times 1/6 on 1 minus, what's the ratio? 2/3. That's 6 on 1/3, which is 6 times 3 on 1, 18. So there you have it. Again, not truthfully 18, but so close to 18 that it rounds to 18. It'd be worth trying. I'll bet by 100 it rounds to 18 as well. Okay, so is this possible? Yes, it's possible because r is negative 0.2. That's between negative 1 and positive 1. So we can go ahead and find this. We can say the sum of the first infinity the first infinity. The sum of all terms in this sequence is the first term. When we put in 0, negative 0.2 to the 0th is 0 times negative, no it's not, negative 0.2 to the 0th is 1 times negative 10, negative 10. On 1 minus the ratio becomes 1 minus negative 0.2 or 1 plus 0.2. So I just need negative 10 divided by 1.2. And I'm going to add the 8. I know it's negative 8 point something, and I know that you guys know that's negative 8 1/3, but I'm going to add the 8, get rid of it, and math fraction. Negative 8 1/3. And here we just have to work for our common ratio. Let's first, I guess since it's saying possible, we better make sure we have a common ratio. 5 divided by negative, nope. 6 divided by, and one more time, negative 6 divided by 5. Negative 1.2. Let's see. Negative 25 on 6. Yeah, that's not what I wanted to do. I did want 5 divided by negative 6. And now I want negative 25 on 6 divided by 5. So far, so good. And now I want 125 divided by 36 divided by negative 25 on 6. And we got a common ratio, and I'm going to math fraction that. Negative 5/6. So, of course, negative 5/6. So our common ratio is negative 5/6. This is, ... this is possible. Can't stress that enough. If it was negative 6/5, it wouldn't even be possible. So our sum of the infinity terms is the first term, negative 6, on 1 minus negative 5/6. That's 1 plus 5/6. That is negative 6 divided by 6/6, and 5/6, 11/6, or negative 6 times 6 on 11, or negative 36 on 11. It's terrible. Negative 36 on 11.